Yeah, welcome to the exercise class for quantum physics for non-physicists course. So again, like a few trivia. This class will take place every Thursday. Yeah, my name is Nuriya. Yeah, so you can ask. Maybe I can even start the video myself. But yeah, so you're not so. One of the things is that you're not supposed to hand in any exercise sheets. So the idea is that in each exercise class, I'll give you maybe some recap of the lecture and then the tools which are needed to solve this particular exercise sheet. And then you would come home and you would look at the exercise sheet. And if you still have any questions about it while you're trying to solve it by yourself, then you can always ask these questions on Moodle or send me just an email directly. Great, is now the thing of working? Yeah, so you can just send them to me by email to Nuriya at phys.eth.ch. Okay, and another question that we've been like receiving a lot in this past days is that so the idea is that this is not a course for physicists. I mean, if you're a physicist, you can still take it because it would be a bit of a different approach to quantum mechanics. But the idea is that you don't need any particular prior knowledge in physics to be able to listen to this course. Maybe something that you would need to recap, which I would advise to recap, especially if you don't have such a good memories about it, is some basic concepts of linear algebra. Because essentially, if you look at it, the whole mathematical apparatus of quantum mechanics is just solely based on linear algebra. So maybe that is a thing that you would need to recap. So for our first exercise sheet, we will deal with mostly what we call Dirac notation, which is something that you have to master in order to be able to kind of read the mathematical language of quantum mechanics. So the idea is that we'll be talking mostly about Dirac notation. So the idea is that in quantum mechanics, we basically study quantum systems, and then every system is assigned a Hilbert space. So for every quantum system, we can assign a Hilbert space. So Hilbert space is this generalization of what we understand as, for example, three-dimensional or n-dimensional Euclidean space. So you can just think about it as vector space, which has like a good definition of our inner product, and it also still allows us to, for example, calculate the angles between the elements of the space. Very similar to Euclidean spaces that we probably dealt with before. And essentially the elements of this Hilbert space, they correspond to the different states that the system can be in. And the idea is that, like in the quantum mechanics, we have this Dirac notation, and we say that, for example, there is a ket. So this is called a ket. And this ket is a state which is labeled as alpha, which is an element of this Hilbert space. So in the end, what you can understand the ket as just a vector in the Hilbert space. So for example, if we write ket psi, then this corresponds to the state with the wave function psi of x. Then we have a complementary object, which is a bra. So for each ket vector here, there is a bra vector like this, which is essentially just a complex conjugate of the ket vector, and it corresponds to the complex conjugate of the wave function in this case. So and then this is this kind of notation is useful. For example, like if you want to calculate the overlap between two states, which you can intuitively understand as a measure of how similar two states are. So then we have, for example, state psi and state phi. Then you can just calculate the bracket of these two states, which for this coordinate representation would just correspond to this kind of integral. Okay, so now let me kind of go a bit deeper into analogy. What is exactly the analogy with the vectors here? So as I said before, so every quantum system corresponds to the Hilbert space, and the elements of this Hilbert space, they correspond to the ways we can characterize different states of quantum systems. However, let us look at this Hilbert space, and we know that for each Hilbert space, it is a complete space, so we can choose an orthonormal basis. Suppose that this basis, we label the elements of this basis as i's, and then if each element of this Hilbert space can be written down as just a superposition of the elements of this basis. This is just according to the definition of the basis, right? So suppose that we have the elements psi, which belongs to this Hilbert space, and for example, which corresponds to the particular wave function of the particle psi of x, and then we can write this out just as a superposition with some coefficient, say I, of the elements of the basis. What this means physically is that if we assign, if each element of the basis has corresponds to the particular wave function phi I of x in the position basis that we've chosen, then this essentially means that we can represent our physical wave function in this position basis psi of x as just a superposition of these basis wave functions. So this is kind of physical meaning of this decomposition. The basis is orthonormal, which means that for elements of this basis, it is true that their overlap is 1 if and only if it's the same element. So this is otherwise. So here maybe like a symbol that you were not familiar before. This is a delta. So delta ij, it's equal to 1 if I equals j and 0 otherwise. And there is also a similar function for continuous variables, which we'll see later. Okay, so this was more like a physical decomposition. And then if we try to write the bra of the psi, so this is just complex conjugate of essentially this, and this is equal to here, and then I turns into a bra. Then the next question is, what is the meaning of these coefficients AI that appear in the decomposition with respect to our bracket notation? So actually the values of coefficients, they can be found by just taking the overlap of the psi with the appropriate state I of the basis that we're looking at. So AI. So let us look at the following equation. So if we take the overlap of the state I of the basis with the state psi that we're looking at, then here we just write out psi in terms of the basis element. And here we take the numbers just out of the bracket. And as we've seen, this here is just delta ij. And here we can write this as sum over j aj delta ij, which essentially leaves us with the only option of I being equal to j, and this is equals ai. So essentially, to find out the coefficients here in this sum, we just need to take the overlap of the function of the psi with the elements of the basis I. So this is very similar to the expansion of a general vector in terms of orthonormal basis, and then to where essentially the list of these coefficients just represents the vector in this given basis. So this is just similar to. So there's a question. Yes. So so there is a question of why we can just take out the sum out of this bracket notation. So I'll show the example just a bit later, actually just in a moment. But the idea is that so the objects the objects which are bra and ket are actually nothing else but certain vectors. So either in a row or in a column. And for example, when you operate with the vectors, then you can take out the coefficients right away. So for example, like if you're dealing with, I don't know, sum over j, like here you have, we can even look at it in terms of matrices, but let's first look at the vectors. So for example, you have vectors A and B, and which belong to I don't know, R3, for example, and then you look at the object, which is a sum over. Actually, let me even do this. And then maybe even without the sum. So first we look at the object, which is A transposed by some lambda by B. So then, because lambda is just a number, you can just take it out here, and then you can just consider lambda separate from the multiplication between A and B, which are the vectors. And here the idea is similar. So because A and J are actually just vectors which have a particular representation in the basis that we're considering, then and the AJs are just coefficients. Yeah, never mind the sum, because like you can just write the sum as the sum of the particular elements of the sum, and then for each element of the sum you can take the AJ out from this bracket relationship, and hence we can just always operate the normal numbers that we have kind of separate from the Bryan-Kett notation. Does it make sense? Okay. So this is very similar, as I said, to the expansion of a vector in terms of particular basis. Okay, so maybe now it's good to give an example. So this is a very simple example. So suppose that we are dealing with a two-dimensional quantum system. So an example of such a system you already seen in the lecture, it's the qubit. So to give a more physical example, so the qubit can be just some atom which has two distinct energy levels, and then you know that if you shine the laser with a particular wavelength, then there is a change of population in these levels, and hence you can just label one level as the ground state and another level as an excited state, and then there are just certain operations, like for example this laser with a particular wavelength, that allow you to change the energy state of the whole atom from ground state to the excited state. So this is a physical example if somebody needed that. So but abstractly thinking, just mathematically thinking, it's just a two-dimensional quantum system, and hence it can be described by two-dimensional Hilbert space. And suppose that we choose in this Hilbert space a particular basis which oh, sorry, I got a question. So you gave an example. Yes, so the idea is that, like, yes, you can, of course, be a bit masochistic and choose a non-orthonormal basis. But then you have to be careful with kind of looking at this bracket correlations between the elements of different bases. But of course, abstractly speaking, you can choose any basis you like. It's just like maybe calculating some quantities would be a bit more difficult. Okay. So for this two-dimensional hyperspace, we just choose an orthonormal basis, and label the states of this basis as 0 and 1. You can think of 0 state as the ground state and 1 as an excited state. And then let us consider, just as an example, a state psi, which would be a superposition, which would still live in this Hilbert space, but it would be a superposition of the states 0 and 1. Okay. Then now we will write the state psi in a vector form. So in a vector form in the basis 0, 1. So psi in the basis 0, 1 as a vector takes the following coefficients. So this is the bra, and then sorry, this is the ket, and then the bra psi would be just the complex conjugate of this, which means that for the vector and just for an arbitrary matrix, the complex conjugate would be that you take the complex conjugate of each of the elements of the matrix, and then you transpose it. But in this case, like since we're using the real coefficients, then this would be just this row vector like this. Okay. Then another example, which we also connected to the state here, is that okay, we've chosen this basis 0, 1, right? But we could have chosen any basis in this two-dimensional hyperspace. And the idea here is that the vector representation of this particular state, it heavily depends on the basis you've chosen. So another example, so let's say this is the first basis that we've chosen. Let us choose another basis, which is also quite, you'll see it quite often during the course, which is called a plus-minus basis. And the elements of plus-minus bases can be expressed in terms of the elements of 0, 1 basis in the following way. So plus is just 1 over square root of 2, 0 plus 1, and then minus is 1 over square root of 2, 0 minus 1. In this basis, we can easily see that actually psi, which is just 1 over square root of 2, 0 plus 1, is just the plus state. Which means that in this basis, psi in a vector representation would just look as 1, 0. Because it would be just 1 by plus 0 by minus. And this example again highlights that while the state itself always lies in the same Hilbert space, and the state itself has to be understood as more of a physical quantity, or alternatively something that represents the state of our knowledge, while the vector form, which is here or here, is something that we write with respect to the basis that we choose to describe our Hilbert space with. So again, the idea here is that state is physical, but the representation of the state is dependent on the basis that we've chosen. Okay, maybe I'll write it here. So, so psi is a quantum state, and its vector representation, or alternatively, if we're looking at the continuous variables and if we're looking at the position, then psi of x is its wave function in the kind of this x spaces. So this is, you can think about the classical analogy with, for example, the velocity of the particle. So the velocity of the particle is this vector which just exists in the R3 space, like in our usual 3D space, and then it depends on which axis you choose in order to write down the components of this vector. So this is, while this is a physical physical quantity. This is just a particular representation. So just before this, we were talking mostly about the idea of like more of this discrete basis that we have. And the example that I've given was exactly for the case when we were dealing with the discrete finite dimensional Hilbert space. However, for example, this is not always the case. So for example, for the position of the particle, position, as we know, is a continuous variable, and then essentially then the state of the position, which describes the position of the particle, it lies in the infinite dimensional space. And just as an example, let us consider a quantum state where a particle is known to be exactly at the position x0. So essentially, like, we have x-axis, then we have this position x0, and we know that the it's exactly at x0. See, so then the corresponding ket is, we label it as x0, and the wave function then is described by the Dirac delta function. So delta of x minus x0, which is equals 0 when x is not equaling 0, x0, and otherwise if x equals x0. So this is an object which is meant to describe a function which has a particular one peak at x0 position, but is equal to 0 at all other points of the x-axis. So this is a very so for someone who hasn't seen this before, this might seem to be like a peculiar construction. However, what I have to kind of admit to is that the way, if you have seen this construction before, for example, in functional analysis, or okay, in other courses, maybe mathematical courses, the way that physicists tend to use this function, it usually gets mathematicians very angry, because for mathematicians this is not exactly a function, but it lives in the other space, which actually only acts on the functions. But however, as we are physicists, we are free to put this function into the integral, and we just have this physical intuition of understanding this function as something that, for example, first you take the function which is just somehow concentrated around the x0 on x-axis. So this, for example, can be just a simple Gaussian. And then you just essentially reduce the width of the Gaussian, such that, and in the limit, when the width goes to 0, you actually get this delta function, which is peaks around the x0, the value of x0. So it's just infinitely sharp, like at x equals x0. Okay, so this was our description of the wave function which corresponds to this x0 ket. Then let us consider some normal wave function psi. Normal, I mean that it's not like delta-like. Maybe it's somehow spread in space like this. And let us consider the overlap. Something that we already done this before in a discrete case, but now we're just doing it in the continuous case. So we look at the overlap of the x0 with psi, and then the overlap can be written as this. So essentially, we just substitute the so we just substitute the sum that we used before in discrete case with the integral, and this equals by definition of the delta function to psi of x0. Well, again, physically, you can see that since delta is equal to 0 at all points except for x0, then actually the only point where we would care about the value of the psi is exactly the x0. Okay, so then we can see that the relation, in this case, the relation between the ket and the wave function is psi of x equals the overlap between x and psi. And this is again similar to the basis vector decomposition analogy that we made before. So psi ket of psi is just a physical object, and then you want to decompose it, so to find its representation in the x spaces. And then what you do both in a discrete case and in the continuous case, you just look at the overlap of this ket with the bra representation of the basis. And then you get essentially the how this physical object, the wave function, looks exactly in this particular basis, here the position basis. And then you can, of course, plot this wave function according to the values of x. So essentially, then psi of x are just coefficients of the vector psi in the basis x. So we can just write psi as this decomposition. And this is what we call position space representation. So this was all very mathematical. To give it a bit of more physical feeling, so physically what this means is that psi of x modulus squared dx is the probability to find the particle, or the system, to find the system between x and x plus dx. And it is generally the so it's the probability density, essentially, it's psi of x modulus squared. Okay, another concept that I want you to introduce to are the operators. And mathematically, an operator is just a function over a space of a physical state. Yeah, sure. I'll be talking, and then you can copy here still. So operators are just functions over the space of physical states, which map the space of physical states onto another space of physical states. And there are different types of operators, and then we'll get into this further in the course. But generally, mathematically, we can just say that an operator, and we usually mark them with the hat. Q, for example, it acts on the ket alpha, and it gives us another ket beta. So acting on one ket, it gives another ket. In terms of analogy with the vector spaces and vectors, alpha and beta are just vectors belonging to maybe the same, maybe different Hilbert spaces. Then in any case, then Q can be represented in terms of the matrix. So you say like this vector space analogy. Q is essentially can be represented as like this matrix with the elements Q, I, J. But again, this matrix is always written down with the respect to the particular basis that alpha and beta are written in. Okay. Then some states are eigenstates of the operators. So this means that if Q acts on the state alpha, then essentially it just gives you the multiple of alpha, of the original state. Physically, operators correspond to different observables, different quantities that we can measure in the lab. So for example, we will see the operator of position, we will see the operator of momentum, the energy, and so on and so on. And for each of these observables, given a particular wave function, we can always we can always write down the expectation value of this observable. So for example, we have a quantum system which has a particular which is in a particular quantum state, and then we want to measure a certain observable, for example, energy. And then if we calculate the expectation value of this observable, then this would be the result that we would be most likely to get. So the expectation value would be Q. It's calculated this way. And then if you write it out in terms of particular representation in the X spaces, then you get this. Yeah, and keep in mind that, again, as I said, while the observable or the operator itself is a physical quantity, its representation and the way it acts on the functions or vectors in different representations can be different. Okay, so as an example, let us look at the position operator, which we label as just X hat. And naturally, the state X is an eigenfunction of position operator with the eigenvalue X. So if we act with the operator X on the ket X, on the state X, then we essentially, what it gives us is just the value of the position by X. So in this sense, you can even understand the position basis as just the basis of eigenvectors of the position operator. Then let us see how it acts on a wave function. So suppose we want to apply the operator x to the arbitrary quantum state psi, and what we want, and this is a very abstract kind of equation here, and again, to emphasize the way we write this as an operator x acting on the state psi, this does not in any way reflect the particular representation that we'll be using for neither of these operators. So and now we want to see, actually, in order to be able to calculate how exactly this operator acts for a particular representation, here the position basis, we should write down we should see what are the, let's call this phi, for example, and we should see what are the what is the representation of phi in the position basis. And as we've seen before, everything that we have to do for this is to look at the overlap of the position basis elements with this new wave function, new element, phi. Okay, so let's look at this. So this will be x psi. This gives us x bra x. Yeah, it would give. Yeah, ideally we should write x conjugate, but since positions are real numbers, then yeah. Then what we get here is x psi, which is just x multiplied by psi of x. Okay, so what we've gotten from here is that actually the way the operator of position acts on the quantum state in the position basis can be described as just multiplying psi of x by x. Okay, so for the position basis, the position operator is just the function x, which is here. Okay, this is not always the case. We'll see it just in a moment with the momentum basis and the and how it looks like in the position basis, and how the momentum operator looks in the position basis. Okay. So now we go to the momentum basis. So now, up to now, we were only talking about the position basis that we can choose in this infinite dimensional hyperspace for, for example, particle moving in moving along the line, or particle in a box, and so on. However, one can also ask themselves a question whether we can choose some other basis in this infinite dimensional space, Hilbert space, which we of course can. And then we choose it and we call it P, their basis. And we can choose the basis such that it would be mutually unbiased to the position basis, which means that the overlaps would be the same, or the absolute values of the overlaps would be the same for all x prime, p prime. And if you choose such a mutually unbiased basis, and you choose it in such a way that p equals some k, say e to the power minus X. And the new elements of the spaces would be expressed via the elements of the position basis in this particular way. Then this basis is called the momentum basis. So in the exercise sheet, there is one exercise which is devoted to this. And there you have to kind of find I already wrote the coefficients out here, but so you will need to find the coefficients in this transformation via the normalization condition, and also show that indeed these two bases are mutually unbiased. Then this basis is called the momentum basis, and it turns out so that it can be physically understood as just representation of the wave function in the momentum space, as opposed to the representation in the position space that we just looked at. Okay, so then in this basis, again, we do the same thing. The representation of psi tilde of P would be just overlap of the position basis elements with the wave function that we're trying to study. So this is a momentum space representation of psi. And again, the physical meaning is the same as for the case with the position. So psi tilde of P modulo squared dP is just the probability of finding of measuring that the particle has momentum P between P and P plus dP. Okay, and analogously to the considerations before, we can introduce the momentum operator P, which this is a hat, which would acting on the psi tilde of P, just act as act as a normal function P. So P by psi tilde of P. Okay. Following from the connection between the basis elements of momentum and position basis, as written up there, it can be shown that actually for the representations of the same quantum states, but in terms of position and momentum wave functions, they have a similar connection, which is just a Fourier transform. Okay, and now I think a good example, like a good question to ask here is that, okay, so we have this kind of momentum operator, which acts in this particular way when for when the quantum state is represented in the momentum basis. Now the question to ask here is that okay, but what if we go back to the position space representation, and then we would still want to kind of be able to act with this operator, and this operator, as the same as the quantum state, it exists beyond like any representation. So our question here is that, like, I don't want to, every time I want to apply position, every time I want to apply momentum operator, I don't want to go back and forth from position basis to momentum basis and so on. So I just want to find representation that this momentum operator has in the in a position space representation. Okay, this we can do. So the question here that we ask is, what is the form of the position of the momentum operator in the position space? So what do we need to do for this? So we just need to take our abstract action of our operator P, which is a momentum operator, on the quantum state psi. Okay, and then what we need to do is we need to write down the representation of this abstract formula in the position space. Again, for this, what we need is we need to look at the overlap with the position basis elements. So again, like maybe to make it a bit more clear, let's label this as phi. Then to find out how phi looks in the position space, we just need to look at the overlap with the elements of the basis of the position. So x phi, which is x p psi. Then we do a particular trick here, which is the following. So we can notice that because of the because of the normalization requirement, actually the following PDP equals identity. So we can just kind of insert it between the brackets, because we can always insert the identity. So here, then we would just get TP. So this is a very common trick to do when dealing with brackets. And why is this useful? Because suddenly we don't need to act with the P operator on the psi, but we need to act with the P operator on its eigenstate P, which makes our life very easy. So then we know that the way it acts, it just gives us the P ket back with some coefficient P. We also know that P psi just gives us the representation of psi in the momentum basis. So this is essentially just psi tilde of P. So what we get here is then integral P psi of P x P dp. And then for overlap, we just we can just use, and you can repeat this trick later. We can just use how the basis of the momentum and position kets relate with this Fourier transform, and then essentially this would give us just the following over 2 pi. Then using the fact that psi of x is just a Fourier transform of psi tilde of p, we can rewrite this integral in terms of just one operator acting on the function psi of x. And this operator, and you can check it later, is minus I d by dx psi of x. And yeah, so this is easy to remember, easy to see if we just remember that psi of x is the Fourier transform. Okay, so this gives us kind of a peculiar answer in the sense that then it shows us that we can describe the action of the momentum operator in the position space basis as the action of the operator minus I d by dx. So this is kind of in position space. And at the same time, P just acts as P, function P, in momentum space representation. Yeah, so this whole example again supports the view that, so you should understand that there are kind of two distinct worlds. So one world is, in a sense, very absolute, and it just corresponds to observables, it just corresponds to quantum states, and so on and so on. And these things, they kind of exist beyond any representation. And then like the second world, which is more accessible, and that world is not that accessible to us because like we need certain tools to describe this absolute thing, these absolute quantities. And for that, we go kind of to the second world, which is very relative in a sense to the representation that we choose to use. So you can understand it. You can take this also as a metaphor with, so for example, we have different things in the world. Like for example, we have a chair, we have beds and everything, but these things they kind of exist beyond the meaning, beyond the word or the meaning that we give to them in the particular language that we choose. But to communicate and to operate with this kind of absolute things that exist mean, we have to choose a particular language to communicate it to each other, and yeah, also give them different properties and so on. And here it's the same. So we have this operators and states, and then we have to choose a particular representation, and we have to be careful. So we stay in the framework of the same representation when we try to consistently talk about the states or the operators. And as mathematically, again, it's a great analogy of the vectors in the vector spaces. Yeah, in Hilbert space is essentially a vector space. And again, remember back to the linear algebra courses that you probably had, that for the vector space, there is a variety of different bases that you can choose, and then the same operation can look different in a different basis. And here the idea is the same, that you have this operation of applying the momentum operator, and it looks differently depending on which basis you choose to represent your quantum state in. Okay. So I guess conceptually that's done. And now let us go to the exercise sheet that you're offered to solve this week. So it has 3 exercises. So the first exercise deals with the finite dimensional Hilbert space, and it just gives you an opportunity to play around with this Bryan-Ket notation, and it just gives you states, quantum states written in the basis of 1, 2, and 3. So we suppose that we have some 3-dimensional system. And then you have to go to the vector representation of this Bras and Kets, and then calculate some overlaps, and also use the fact that the basis is the basis is also normal, and that all states have to be normalized. So this is just quite a simple exercise just to get you going with this Bryan-Ket notation. Then the second exercise is a bit similar, but it deals with continuous infinite dimensional hyperspaces. And there you have, there you see the exact connection between position and momentum basis. And also there is a particular example where you will be given a representation of the quantum state in the position basis, and then you have to go to the representation in the momentum basis. And the example is the ground state of the particle in a box. So if you have a box with a length L, then the ground state of the particle, the wave function of the ground state in the particle in a box in the position representation would be proportional to the cosine by x over L. So first you'll need to kind of find the normalization for this wave function, then go to the its representation in the momentum basis, and then also calculate the expected values of the position and momentum operators. So it deals also with the measurement in the end. So what is the expected value of the position if you measure the position, and then what is the expected value of the momentum if you measure the momentum. Since I already explained to you, you've seen already how the momentum operator looks like in the position representation. You may already calculate its like the expectation value of the momentum just using the position representation. So, but you can also alternatively just use the momentum representation directly. So again, expected values for the position, it would be just if we squeeze essentially the operator x between the Bryan-Ket psi, and in the position representation it would look like this. And the momentum is the same here. And here, there are two ways in this set. So first way is just to write everything in the position, in the momentum representation, sorry. And then we know that in the momentum representation, the operator P is just the function P. Or alternatively, you can also stick to the position. Then you would still need to keep this as an operator. But we already seen how this operator acts. X dx. The results obviously are the same in both cases, but if you want, you can check. Okay, and the third exercise has to do with the Bloch sphere. And this notion is very particular to the fields of the fields of quantum information or quantum computing mostly, because a Bloch sphere as you already heard in the lecture, it's a very good way to visualize what is the state of the qubit. So the qubit is, as I already mentioned, is a two-dimensional quantum system. So the states of the system, they live in a two-dimensional hyperspace. So essentially, it means that if it lives in a two-dimensional hyperspace, then if we call the elements of the basis as 0, 1, we denote them as 0, 1, then we can write any possible quantum state of such a system as alpha 0 plus beta 1, where alpha, beta are some complex numbers, and of course the normalization condition also holds. And usually it's very difficult to generally to imagine, like, oh, there are two complex coefficients. How do I imagine this to myself? How do I visualize it? Here in this particular case, it's easier because actually you can write any such state as in the following way. For some phi and theta, which are the angles. So phi is from 0 to 2 pi, and theta is from 0 to pi, I think. And in this case, every such state can be just characterized by these two values, phi and theta, which are real. And then essentially every state just corresponds to some a point on the three-dimensional unit sphere. Yeah. And then you'll see that actually there are certain operations like rotations, which can be applied to the state, and they would correspond to the rotations with regards to this sphere. Yeah, and in this exercise, you also see that, like, again, the rotation is an operator, right? But we're dealing with a discrete system, which is two-dimensional, which means that in this case, this operation just corresponds to 2 by 2 matrix. And in this exercise, you'll be given this 2 by 2 matrices, which act on the states, and you need to kind of find, just apply them to the states that you're given and see what you get in the end, which states they are transformed into. Okay, I think I'm more or less done for today. Are there any questions? There is a question. What is the physical interpretation of the relative phase? So the question is, what is the physical interpretation of the relative phase in a qubit? Yeah, let me think. So I mean, like, for example, if we take again the state, sorry. Two phase. So I think here, yes, here it would be useful to think of the following example. So for example, imagine that you're dealing with the state psi right, and then phi can take any value from 0 to 2 pi, let's say. And then, of course, if you're measuring in the basis 0, 1, then of course you can see that if you look at the overlap of the state psi with 0 and 1, then essentially the results that you get will not depend on this phi in any way. However, if you measure in another basis that I also mentioned, in this plus minus basis, then phi does play a role. So for example, let us calculate like what is the overlap of plus and phi, right? It would be also a good exercise. So we write plus and we write phi. Sorry, we write psi. We take both of the square roots out. Then here we have 0, 0 plus 1, 0 plus I 1, 1 plus 0 to the phi 0, 1. Then this is 0, this is 0. Then we are left with 1/2 0, 0 plus 1/2 e phi 1, 1. This is 1. This is 1. And we're left with 1 plus e to the power I phi over 2, which means that the probability of measuring plus, if you have the initial state of psi, which would be just given by the this absolute square, be 1 plus e to the power I phi squared. So essentially, I guess like here the relative phase would come out. So again, the idea here is that of course this relative phase does not play any role if it's kind of the 0, 1 basis. However, if you try to change the basis, the same as you go from the position to the momentum, but just here you go from the 0, 1 to plus minus basis, then if you try to measure in this plus minus basis, then actually the phase would play a role. Does this answer your question? Okay, good. Any other questions? Okay. So if you have any follow-up questions, you can still ask me in the email or in the Moodle. So this recording will be hopefully posted today on YouTube. So if you want to revisit it, then you're also welcome. Okay, cool. Have a nice day. Bye.